In the more esoteric fields of programming, you'll often hear people refer to types with the sort of mathematical notation: product, sum, algebraic, etc. These might sound abstract, but you actually use them every single day, especially product types. So in this video, I'm just trying to explain them to people who don't actually care about Haskell. Just a little note, the language used in this video is just for demonstration. It's not a real language. Its goal is to keep a familiar C-like syntax while being able to represent these advanced types. Product types are first, because they're what you're most familiar with. You probably know them under different names though, like structs, classes, records, and tuples. A product type is any type that has several fields that all exist separately. So where does the name product come from? Well, consider a type like this. It represents two different flags about an enemy, each of which can either be true or false. If we look at a little graph of this type, we can see that there's 2 possible states for each field, and 4 possible states for the entire type. We can take this a step further, replacing the booleans with 8-bit integers. We can see that we have a 256 by 256 grid, giving us 65,536 total points. And that's the key with the term. The number of possible values of this type is the product of the number of possible values of its fields. In type theory lingo, the number of possible values of a type is called its cardinality. So the cardinality of a product type would be the product of the cardinalities of its fields. If a product type is a type whose cardinality is the product of its field's cardinality, then you can probably infer what a sum type is. Still, I wouldn't blame you for not being able to guess exactly how that works in practice. What does it mean for a type's cardinality to only be the sum of its fields? Well, it means that the fields don't all exist separately. Instead, the fields function as options or variants, a sort of list of possible types that the value can have. For example, this type, it could be an integer or it could be a string. So its possible values are all of the possible strings plus all of the possible integers. It's pretty likely that you've used this sort of thing before. A lot of languages have unions, which mostly encode the same concept. Some languages, like C, don't automatically tag unions, which means no data is stored to tell you which variant is currently being used. So, what are the actual uses for a sum type? Well, there's a ton. Generally, any time where you want to explicitly specify some relation between types, a sum type is a good idea. You could use one to represent the different types of enemies in your game, or the different types of nodes in a tree, or the different states in a state machine, or even the different ways some function could fail. The benefit of this over something like interfaces is that you concretely know exactly what variants exist, and what their data is, so handling them happens directly inline, rather than relying on delegating to a shared set of behaviors. This has performance benefits in a lot of languages, and just generally makes the code easy to reason about. Not every problem fits this model, of course, but it's certainly a nice tool to have in your head. We will actually get into traits later on, which are a sort of advanced interface, so they really are both independently useful. Now, let's get into the more advanced stuff. First, I'll talk about ADTs. ADT stands for algebraic data type. As the name somewhat implies, it's a combination of sum and product types. If you've used Rust before, these are your enums. I'll be shifting away from the word fields here, as that terminology doesn't really make sense. So these are the type's variants. Each variant has a name, and each variant is itself a sort of product type. This means that it can have regular fields, like this. It's also extremely common to have tuples here. Combining sum types and product types gets us a very expressive way to represent all sorts of things, because we directly associate data with each variant. This makes it trivial to do things like attach information to an error or model more complex state machines, all entirely inline. While you could obviously recreate the same effect with a regular sum type whose variants are all regular product types, there are definitely some notable advantages to flattening it all into one type. The main one being that you can often have a nice pattern matching syntax, since you know your variants are just some number of different product types. It also greatly simplifies actually writing the type, because you can do it all right inline. The reason Rust calls these enums, by the way, is that they effectively are. If you choose to not attach any actual data to any of the variants, you're just left with a value that can be one of many different named cases, which is exactly what a standard enum is. ADTs aren't perfect though, and that's where GADTs come in. They're pretty complex, and only a small handful of languages actually have them, but a GADT, or Generalized Algebraic Data Type, functions as an extension to ADTs to make them even more expressive. I'll showcase exactly how they work with the most common example, an expression. We'll start by trying to use a regular ADT and seeing exactly where it falls short. Admittedly, this is a somewhat contrived example, but you'll see it in a lot of places online, and it really does represent the problem and the solution very well. Consider a structure for an expression inside a programming language. It's some combination of different sub-expressions, so the type may look like this. We have some base variants, and we build other types on top of them. The issue, in theory, is that this could represent invalid ASTs, like adding a boolean to a string. This could be a problem if you wanted to execute this program by walking the AST, since there could be a runtime type error that you didn't catch. Embedding everything into the type allows you to verify that you have valid data. The idea of GADTs, then, would be a way to extend ADTs to ensure we can't represent these kinds of invalid expressions by adding constraints to the variants. The first step would be to make our type generic so that it represents the type that it actually evaluates to. This allows us to specify things like addition only working on numbers in theory, but we need a GADT to enforce it properly. The key thing about a GADT is that each variant can describe when it is a valid state, and the type system can properly apply these constraints. We can specify that Boolean literals are for expressions of Booleans, for example, and number literals are for expressions of numbers. Then, we could specifically allow things like addition between numbers, or comparing numbers, and properly specify their types. This works great for simple cases, but sometimes there's a need for more complicated relationships. For example, with addition, maybe it's not just numbers that can be added. What if we wanted to be able to add strings? Maybe we could duplicate our add variant, but ideally we'd be able to use the same variant for both, using some mechanism to represent which types can be added to which types and what they produce. The right way to do this is with traits, or type classes as Haskell calls them. A trait isn't exactly a type on its own. It's basically an attribute that you can apply to types by implementing the trait for that type. A trait will specify some functions that it requires to be implemented, and then a type can implement that trait by providing an implementation for those functions. In our case, we'll make a trait that's generic, so that we can specify what types the implementer is being added from. We'll create a trait that neatly represents the operation of addition, where we're generic over the types on the left and right hand sides of our expression. Then, we can make this a step further by making our variant generic, using a where clause to specify that T must implement add from left-right. This means that if I tried to create an add with two values of type x per L and x per R, it would only be valid if an implementation of add from exists for that L and R, which makes it impossible to have invalid expressions. That's all for this video. I know it was a bit different than normal. Usually I focus on more low-level topics, but I think this is something that more people should understand. I don't actually think it's that useful, but it's worth learning still. Anyways, like, subscribe, thanks for watching, and goodbye.